Can you hear me?
Yes.
Thank you. Okay, to record. So I remember that when we needed a little bit of matrix notation to introduce matrix notation for multivariable calculus, I presented a few slides about matrix product, basically, okay? So if you remember, of course I don't want to explain these slides again, but if you remember, just to recap the material we have seen already, matrix notation, I introduced the matrix product, which is a basic tool, and I started with the product between a vector and a vector and another vector. One is a row, the other is a column. Then I extended this matrix by vector, okay? And then matrix by matrix, I remember, maybe. No, vector by matrix by vector, okay? Just to introduce quadratic forms. I guess you remember this. So basically, we have only seen the matrix product. Now, I'm going to show you a few more things. Matrix by matrix, and then matrices with particular structures, and the way they can be problems involving these matrices with particular structures can be worked out in just a few minutes. And then I will introduce something more about matrices, what is needed to use matrices for dynamic analysis, which means determinants, a very basic case of solution of linear systems, and eigenvalues and eigenvectors. If there will be some time left, I will show you a summary exercise on matrices, which is what I require for the examination, okay? Which is basically being able to work out matrices to compute eigenvalues, but also to see some structures and to work out simple operations between matrices, products and quadratic forms, basically. Also, there are other concepts involved. For instance, when dealing with determinants, I will also show you what the inverse matrix is, okay? So it's just focus on structures, not on difficult computations, structures. So this is the basic set of slides. I have uploaded a basic set of slides, it's 10 slides, 12, and then another set of slides, which is about 100 slides, which is the extended version, okay? So you don't need to learn everything about the extended version. Only if you have time and you want to understand more, you can just look at the extended version. So basically, if you remember, of course, you all know that a matrix can be regarded as an array of numbers arranged on rows and columns. This is the general representation of a matrix. This is a M by N matrix, M rows, N columns. For instance, this one has 2 rows and 3 columns, so it is a 2 by 3 matrix. Okay, this is the definition, but never regard a matrix as an array of numbers. It's not really a good strategy to work out problems with matrices. Regard them as a unique mathematical object, and if you want to decompose, to see the structure just, for instance, as a certain number of row vectors or a certain number of column vectors. So look at matrices as ordered sets of vectors, either rows or columns, okay? Not just as an array of numbers. So basically a matrix is a unique mathematical object. Square matrix has the same number of rows and columns. There are very particular matrices that are vectors. They are matrices of dimension, 1 by n or n by 1. 1 by n means 1 row and columns, and they are row vectors. Any questions? Okay, please turn your microphone off. And the column vector has n rows and 1 column. There are basic matrix operations. The first one, there are 2 basic operations. One is the so-called product between a matrix and a scalar. A scalar is a name to denote a real number in the world of matrices, especially when this real number is something that multiplies a matrix, okay? So if I have this matrix and this scalar, alpha times A, scalar by matrix, is just the same matrix with each element multiplied by 1/2. Okay? So this is the product between a matrix and a scalar, which is very different from what we call the scalar product. The scalar product, if you remember, maybe we've seen this already, the scalar product is the product between a vector and another vector, if you remember. In the first set of slides I presented to you, I've shown to you that if I want to multiply a vector by another vector, the first one must be a row and the second one must be a column. But basically what we do is to multiply 1 times -1 and 2 times 3 and to take the sum, okay? So we could define another operation in the world of vectors, which has the same practical result. Take 2 vectors, don't worry whether they are rows or columns, they just must have the same dimension, multiply element by element, and take the sum. 1 times -1 plus 2 times 3 equal 5. If I regard this kind of the product between vectors in this way, this is a different operation. Here I don't worry about structures, rows, columns, okay? And this is called inner product, dot product, or scalar product, and it is denoted like this. So if I have 2 column vectors, I can do that. But if I want to regard them as particular cases of matrices, in order to do the same operation, the first one must become a row. So I have to write X transpose times Y. So it's just a matter of structures and notation, but the practical effect is the same. So one thing is the scalar product between 2 vectors, called also dot product, inner product. And another thing is the product between a matrix and a scalar, which is a number. So 2 very different things. So this is an example. What about the sum of 2 matrices? Of course, 2 matrices can be summed up with one with another if they have the same structure, same number of rows, same number of columns, and the result is a matrix that in each position has the sum of the corresponding elements. So it's really easy. The sum is computed element by element. Have these 2 matrices. What is the sum between these 2 matrices? First of all, I can compute the sum because they have the same structure, 2 by 2. Second, this element, for instance, in the sum is -1. This one is 4. It's 1 plus 3, and so on and so forth. Okay. What is the linear combination of 2 matrices? It's the sum of the 2 matrices. Possibly each one has been previously multiplied by a scalar. So if I have these 2 matrices, the same structure, of course, and I write, one is A, the other is B, and I write A minus 2B, this means compute the sum between A and B, which has previously been multiplied by -2, okay? So I do this. So this becomes -2 minus 2, 0, 0, 4, minus 6, and then I compute the sum, and this is the result. Linear combination of 2 matrices. Linear combinations are particularly important in linear algebra with regard to vectors, okay? Linear combination of vectors is exactly the same. We have vectors instead of matrices, very typically column vectors. But the concept of linear combination is the same. Then we have matrices with particular structures, the zero, null matrix, the identity matrix. This is quite important. The identity matrix is quite important. It plays the same role as number 1 in the multiplication between numbers, okay? What is the identity matrix? Is a matrix having all 0 elements and 1 in the main diagonal. Now, I'm going to show you a few examples of matrices with particular structures, but I want to, they are already written here and in the next page, okay? But of course, I want to show you a few things which is much better explained by writing something now. Okay. So this is, for instance, denoted by I2, identity matrix of dimension 2. Identity matrices must be squared, okay? So an identity matrix is squared. There are no rectangular identity matrices. Suppose that I want to multiply 1/2 times this identity matrix, that is 1/2 times 1, 0, 0, 1. We know what is the multiplication of a matrix by a scalar, and the result is, of course, this one. Of course, this is not the identity matrix, but it is very similar in structure. It has all 0 elements except the same number in the main diagonal. So it can be regarded as the product between a scalar and an identity matrix of dimension n, if I have the product between a scalar and the identity matrix of dimension n, which is this one, okay, all zeros except alpha in the main diagonal. This is called scalar matrix of dimension n. Scalar matrix because it plays the same role as a scalar in the matrix multiplication. So this is the identity matrix. A constant times the identity matrix is a scalar matrix. But now I may have simple structures similar to this one, but slightly more general. For instance, 1, 2, 3, 0, 0, 0, 0, and 0, 0. This is not a scalar matrix, but it is called diagonal matrix. Only the elements in the main diagonal are possibly different from 0, but they are not equal to each other. Diagonal matrix. Also, these diagonal matrices have some interesting properties. For instance, it is really easy to compute the determinant of these matrices. And next, we have other matrices with a very nice structure like this. Not the same, 3 for instance here. So look at these matrices. We have a main diagonal. All the elements above the main diagonal are possibly different from 0. All the elements in the main diagonal or above the main diagonal are possibly different from 0, but the important feature of this matrix is that the elements below the main diagonal are all 0. This is called triangular matrix. In particular, this is upper triangular, because it is only the upper part is filled with possibly non-zero elements, okay? This is lower triangular. Okay, so this is the main diagonal. It is possibly filled with non-zero elements in the lower part, but the important thing is that the upper part is all zeros, okay? It doesn't matter whether there are other zeros, also in the lower part or in the main diagonal. The important property is that the upper part is made up of all 0 elements. This is called lower triangular. So the feature is that, what is an upper triangular matrix? It is a matrix where all the elements below the main diagonal are zeros. We don't require anything about the elements above the main diagonal. They could be all zeros, okay? They could also be all zeros. This is an example of lower triangular, which has a symmetric definition. Triangular matrices have very important properties, and it's possible to simplify a lot the computations of the determinant, for instance. Okay. Now, it is all written here. The matrix multiplication, we have seen only the multiplication between a matrix and a vector. Now, the matrix multiplication is a multiplication between a matrix and another matrix, in particular between a matrix and a vector. But what is really important here is that you understand the structure of the matrix multiplication, which is performed row by column. So let me just show you an example. This is a 2 by 3 matrix. This is a 3 by 2 matrix. It is possible to compute the product. The fact that it is possible to compute the product is number okay? So first, we can perform the product between 3 is equal by 3 here, 2, 3. What will be the dimension of the result? It will be a matrix. It will be 2 by 2. So it will be something with 4 entries, 2 rows, 2 columns. Now, if you want to multiply, you know what the product of a vector by a matrix is. So suppose, for instance, that you want to compute the product between this vector and this vector, vector by vector. 1, 0, 2 times 3, 2, 1 is equal to, you can also write this as a dot product if you like, 3 plus 0 plus 2 equal to 5, okay? Now, remember that we compute the matrix product row by column. If you remember this, you understand immediately how the product between matrices works. Because how many rows do you have here? 2. How many columns do you have here? 2. How many row by column products will be necessary? 4. 2 times 2. So this times this will fill the first element 1, 1 in the new matrix, okay? This. First row by second column will be reported here. The element of position 1, 2, and so on and so forth, okay? So here I have 5. Now, fill the second position here, 1, 0, 2 times 1, 2, 2. It's 1 plus 0 plus 4. No, sorry, this was 3. Okay, 3 plus 2, 5. Okay, this is again 5. It is 1 plus 0 plus 4. It is again 5. Now, second row by first column, this element, minus 6 plus 2 plus 0. Minus 6 plus 2 is minus 4. Okay? Position 2, 2. Second row by second column. Minus 2 plus 2, which is 0, plus 0. 0. This is the product. Okay? So matrix product works row by column. And there are some particular cases, of course. Suppose that you want to multiply the identity matrix times this matrix A. This is 2 by 2. And now consider, for instance, this one, which is 2 by 3. Okay, so suppose that you want to multiply this identity matrix by this one. What is the result? Let me perform the product. We can perform the product. It will be a 2 by 3 matrix. 1 times 1 plus 0 times 2 is 1. 1 times minus 1 plus 0 times 3 is minus 1. This times this, 0. It becomes equal to the second matrix here, okay? Why? Because this plays the same role as 1 in the multiplication between numbers. So if you complete your operation, you see that the result is this one, okay? So the identity matrix of dimension n times any other matrix of dimension, of course, n times p, as a result, it has the second matrix. Like for numbers, 1 times A is equal to A, okay? Clear? Identity matrix plays the same role as the number one for matrix multiplication. So it is called the neutral element of matrix multiplication. Another thing, suppose that you want to multiply this matrix. Times a matrix similar to the previous one. Don't start writing computations. This is equal to 3 times the identity matrix times this. Okay? Because this is, oh, sorry, 1. This is a scalar matrix, okay? Scalar matrix means the same scalar times 1. Now, the product between this and this is again this one. So you have 3 times 1, 2, 3, minus 1, minus 3, minus 4. So this is equal to 3, 6, 9, minus 3, minus 9, minus 12. Okay? Okay, so basically, remember that when you have identity matrices, scalar matrices, you can simplify computations with a little bit of algebra of matrices, without computing, actually computing based on the rule of the matrix product. Okay. So matrix multiplication, it is row by column. There are a few remarks. I don't want to. You can follow this. I mean the insights from these remarks by just looking at the examples. In general, the product between matrix is not commutative. It doesn't have the commutative property. Okay? Because there are many reasons why this doesn't work. First of all, I can compute A times B sometimes, but I cannot even compute B times A because of the shape of the two matrices. Remember that in order to compute A times B, okay, the number of columns of A must be equal to the number of rows of B. But this doesn't imply that the reverse holds. Okay? So maybe this is computable and this is not even computable, okay? Also, it can be computed, but they may have different dimensions, so they are different matrices. And one example is very simple. If I have a 2 times 3 matrix, and here 3 times 2 matrix, the result, here it is a 2 by 2, okay? But if I compute, this is A times B and this is C, but if I compute B times A, I can compute it because it is 3 times 2 and the other is 2 times 3, I can compute it, but the result is 3 by 3. So this is another reason why they are not equal in general. And also, if I are square matrices of the same dimension, you can compute both one way and the other way, but in general they are different, okay? The result will always have the same dimension, but in general they are different. So this is basically the reason why. There are a few exceptions. One is when you multiply a matrix by the identity matrix, so you can multiply this order, identity times our matrix, or our matrix times identity, and the result is always the same, okay? So when you compute the product between a square matrix and an identity matrix of the same dimension, the result is the same. And another case, this is important, another case in which the result is the same is when the two matrices are powers of the same matrix. Why is that? First of all, what is the meaning of have a square matrix A? What is A squared? A squared is A times A. So if I have A, which is for instance 1, minus 1, 3, 2, and I compute A times A, so again 1, minus 1, 3, 2, I obtain a result which is 1, minus 3 is minus 2, first element, minus 1, minus 2, this is minus 3, 3, plus 6, 9, minus 3, plus 4, 1. Is that correct? 1 times 1, minus 1 times 3, it's 1 minus 3 minus 2. This is minus 1, minus 2, minus 3, 3 plus 6, 9, minus 3 plus 4, 1. Now, this is called A square, of course. So you can define for square matrices powers with a positive integer exponent, of course, okay? We can define powers. Now, suppose that you want to multiply A, you want to compute A to the power of 3. What would A to the power of 3 be? It would be A squared, this one, times A again, okay? So that would be minus 2, minus 3, 9, 1, again times A. 1, minus 1, 3, 2. Solve this by exercise. So compute A to the power of 3. But now, remember this, A, this is equal to A times A and then times A. The matrix product has a simple associative property. So I can compute A times A first, as I did here, and then times A once again. But I can also compute A times A. So basically, A squared times A, which is what I do here, must be the same as A times A squared. What does this imply? That if all the matrices that I use are square matrices that are powers of the same matrix A, the commutative property holds. Okay? You see here? We have the commutative property. This is another case in which we have the commutative property. There are some very particular cases in which this property holds. It doesn't hold in general. Next, there are some other very useful computations. What is the power? P. P is an integer, 2, 3, 4, 200, of the identity matrix. It's like raising the number 1 to the power of n. The result is again 1. So you can try, raise the power, compute the power 2, for instance, of an identity matrix. The result will be again an identity matrix, of course. What is the power of a scalar matrix? Also this one, you can try with a simple example, a 2 by 2 matrix. Okay, so if you have scalar multiplied by the identity matrix, okay, which means a matrix which is diagonal with all elements in the main diagonal equal to lambda. If you raise this to the power of p, you have this matrix. It is again a scalar matrix where each element in the main diagonal has been raised to the power p. So it's very simple property that can be checked immediately. It can also be proven, of course. And the reason why it works this way is that if you want to multiply, if you have two scalar matrices equal to one another, lambda, 0, 0, lambda, and you multiply this times this, in principle, you can try to multiply. What you obtain is lambda squared, 0, 0, lambda squared, because it is lambda, 0, 0, lambda squared, okay? It's lambda 0, 0, lambda times lambda 0, 0, lambda. So our rule tells us that the result is this one. By the way, here you have that this one, the first factor is lambda times identity of order 2 times lambda times identity of order 2. But these are scalars. We can just multiply one scalar by the other first. and then take the square of the identity of order 2, which is again the identity of order 2, okay? And this is precisely this one. Also, if you have two matrices, for instance, alpha identity of order 2 times beta identity of order 2, they are two scalar matrices, but the constants here are different. Of course, the result will be alpha beta times identity of order 2, and so on and so forth. These simple structures are very useful. The matrix transposition is another operation that we can perform on a matrix. And the operation is very simple, and it is like this. If you have a matrix, just build another matrix in which you exchange the rows of the original matrix with the columns of the new matrix, okay? So A has 2 rows and 3 columns. The transpose of A has 3 rows and 2 columns. The first row of A is the first column of A transpose. The second row of A is the second column of A transpose. Okay? So this is the operation of transposition. Now, what is a symmetric matrix? Which are other structures that are useful. I guess that the symmetric matrix, we defined already the symmetric matrices, okay? But I want to show you one more thing on symmetric matrices. So what is a symmetric matrix? A symmetric matrix has this property. This is symmetric because we may have a given main diagonal, and then the elements that are in symmetric position with respect to the main diagonal are equal to each other. For instance, this is a symmetric, necessarily square matrix. Symmetric matrices are necessarily square matrices. Why is this symmetric? Because apart from the main diagonal, all the elements that are in symmetric positions with respect to the main diagonal, for instance, this is the element A1, 2, and this is the element A2, 1. Symmetric position means exchange the index of the row with the index of the column, okay? All the elements that are in symmetric positions are equal to each other. You see this? You see this? -2 and -2. This is A31, this is A13, and then 0, 0 here. Okay? 0 and 0. Try to compute the transpose of this symmetric matrix. Exchange the rows with the columns. Of course, it is the same matrix. Okay? If you compute the transpose, because the fact that the elements are symmetric with respect to the main diagonal means that if you replace the rows of the columns, you get the same matrix, because here the first row is equal to the first column. The second row is equal to the second column. So this is taken as the definition of a symmetric matrix. A matrix A is symmetric if, and only if, it is equal to its transpose. Okay? So this is the definition of a symmetric matrix, and now there is another important property involving transposition and symmetric matrices, and this is this one. Let me take a matrix with many zeros so operations are easy. Now I take the transpose of this one. This is 2 by 3. This is 3 by 2. The result will be 3 by 2. Compute the result. So this is A, this is A transpose, okay? Compute the result, it is 1, 0, 9, so it is 10. Minus 1 are 0, 0, minus 1. Minus 1, 0, 0, minus 1. 1 plus 4, 5. So apart from the main diagonal, this is a general rule, apart from the main diagonal, the other two elements are symmetric. So basically, if you compute, if you take a matrix A, and you multiply this by its transpose, you always get a symmetric matrix. Of course, also if you do A transpose times A, you get a symmetric matrix. Remember that this can be very different matrices, okay? For instance, this is a 2 by 2, but if you multiply this times this, as the first factor is this, you get a 3 by 3 matrix, which is symmetric. So both A times A transpose and A transpose times A are symmetric matrices. Okay? This is a very important property of symmetric matrices. Next, matrix transposition can be denoted in different ways. We have a notation. This is the transpose of A, but the transpose of A is also denoted like this. Okay? We have different notations. And another thing, there is a very important property of matrix transposition. Suppose that you can compute A times B, in the sense that they have the right shape, the right number of rows and columns, okay? Now, suppose that you compute A times B, and then you want to take the transpose of the product. Compute this, and then you take the transpose of the result. This is equivalent to multiplying the transpose of B times the transpose of A. Okay, so this is the most important property with matrix transposition. So basically, you can try with a simple example, and you see that. So, I mean, the first intuition would be, okay, the transpose of the product is the product of the transpose matrices, okay? It doesn't work in this way. You have to take the inverse order of the two factors. Determinants of square matrices, and then a very basic message on the solution of linear systems. What is the determinant of a square matrix? The determinant is in general, it is a number associated to a given square matrix, okay? So we don't have determinants of generic rectangular matrices, only of square matrices. There are rules, general rules to compute these determinants for matrices of any dimension. Determinants capture very important properties of the matrix, but what you need to know now is that they are numbers associated to a square matrix, so uniquely associated. If I have a square matrix, I have its determinant, okay? There are very simple rules to compute determinants in the case of 2 by 2 matrix and 3 by 3 matrix. In the case of a 2 by 2 matrix with this structure, the determinant can be computed by multiplying the elements in the main diagonal and then subtracting the product of the two elements in the other diagonal, okay? So for instance, for this matrix, the determinant is 1 times 3 minus 1 times 2. The result is 5. The general formula is this one. for a 3 by 3 matrix, one possible way to compute it is the so-called Saros rule. Of course, we cannot, in this case, use the basic rule, but use something similar. You have a matrix, rewrite the first two columns this way, then consider the blue products here and compute the sum of these blue products, which means 1 times 2 times minus 1 is minus 2, okay? 2 times 0 times 1 is 0. 1 times 0 times 1 is 0 again. So you compute the sum of the blue, which are the so-called diagonals. They are diagonals similar to this one, okay? From top left to bottom right. Minus the sum of the products along the remaining diagonals, okay? So minus, this becomes 2, this is 0, and this is 0. So the determinant here is minus 4.
What's the meaning of the determinant?
The meaning of the determinant is basically, I can show you the representation of the determinant for a 2 by 2 matrix, for instance. And a similar representation holds for a 3 by 3 matrix, because we have the geometric interpretation, and then we have to be a little bit more abstract to understand the meaning. But if you have a 2 by 2 matrix, for instance, so you have here, for instance, 2, 1, minus 1, let me say 2, 1, minus 1, 3, for instance. Okay, take the two rows. So the determinant here would be 5 plus 1, 6, okay? Take the two rows, regard them as vectors. Vectors as pairs of coordinates in the plane. Abscissa 2, vertical coordinate 1. So this is the geometric representation of the first row. Abscissa minus 1, vertical coordinate 3. So 1, 2, 3. This is the representation of the second row, okay? Now, regard vectors not as points of the plane, but as so-called geometric vectors. So start from the origin with an arrow and go towards the point. Sorry, this is not the origin, of course. Start from the origin, which is here, and go to the point here, and do the same with the other vector. Okay? Now you can build a parallelogram by shifting this, with a parallel shifting of this like this. Okay? And with a parallel shifting of this like this. Okay? Take the area. This is the determinant. Okay? So it has basically a geometric meaning in, for instance, in a two-dimensional plane. You can do something similar also in the three-dimensional space, because you don't have, of course, a parallelogram, you have a solid, but it can compute the volume, okay? Which is basically the same meaning, geometric meaning, but what is important here is that, I mean, I don't want to show you the theory of geometric vectors, but if you have these two vectors, consider this matrix, 2, 1, 4, 2. What is the determinant, which is denoted like this, okay? A like this, or determinant of A. This is equal to 4 minus 4 equal to 0. The reason why the determinant is 0 is that the two rows are proportional to each other. The second row is twice the first row. If you think of the geometric interpretation, the two vectors look like this, okay? So 2, 1, it is the first row, and this is the first vector. The second row is 4, 2, it is this one. Now, build with an arrow the second vector. If you try to do the same operation, so to obtain a plane area, like in this case, you cannot do that because the two sides overlap to one another, okay? It's like having a very shrinking this, but the area is zero in this case, okay? And this is the reason why when you have two proportional rows, the determinant is zero. The geometric interpretation reflects the fact that the determinant is zero in this case, okay? So what is the area here? You should close your parallelogram in this way, but it is just a line. A line has zero measure in the plane, okay, zero area. So it is zero. So this is one interpretation of the determinant. But the properties of the determinants, apart from this geometric interpretation, turn out to be very important when you want to solve linear systems, okay? So the key for the solution to linear systems is the determinant of the coefficient matrix, or submatrices of the coefficient matrix. So you will see an example in a moment. So I'm just trying to let you know how to compute the determinant in two simple cases, because we will deal with 2 by 2 or at most 3 by 3 matrices. So these are short ways to compute the determinant. There is a more general rule, which is also interesting because it highlights a little bit what is the meaning of the determinant mathematically, I mean, okay? But this is a more general rule, and we don't have the time to study these rules and to focus on these rules here. In a matrix, there is also another important quantity which is important for dynamic analysis, which is called the trace of a square matrix. So basically, you will see that for systems of dimension 2, both the determinant and the trace are important, okay? What is the trace of a matrix? It's just the sum of the elements in the main diagonal, okay? So, for this matrix, for instance, the determinant is 2 times minus 3, which is minus 6, minus 0, minus 6. The trace is 2 minus 3, minus 1, okay? Now, here there is another important property embedded here, which is this one. If you have a triangular matrix, this is a triangular matrix. Its determinant, you can realize this by applying the Saros rule, and even more generally with a more general method, which is called the cofactor expansion method, which is in the extended set of slides I have uploaded, okay? You can see that for a triangular matrix, the determinant is just the product of the elements in the main diagonal. So it is 1 times 4 times 6, equal to 24, okay? For a triangular matrix, the determinant is the product of the elements in the main diagonal. Of course, this holds also for a diagonal matrix, because a diagonal matrix is in a particular case of a triangular matrix. So determinant of A here is minus 1 times 2 times 3, minus 6. Another particular case of diagonal matrix is a scalar matrix. And the determinant in this case is again 2 by 2 by 2. 2 to the power of 3, okay, equal to 8. The determinant of the identity matrix is this answer, 1, okay? Determinant of the identity matrix, it has 1, 1, 1, it is 1. So basically, these are the most simple cases in which it is possible to compute the determinant by just remembering the structure of the matrix. So if I have a square matrix of order n, if A is a scalar matrix of order n, which means that A is equal to a scalar times the identity matrix of order n, the determinant of A is equal to the scalar to the power of n times nothing. Okay, so this is the determinant of our matrix. Okay, in this case, it was 2 to the power of 3, because this is a scalar matrix of order 3. Okay? Clear? Very simple cases that are, however, are very useful in general, I mean. And then the final step is understanding a basic point about linear systems, okay? Here I take some more time because I want you to be able to see immediately the structure of a linear system and to see immediately how this can be expressed in matrix notation and to understand the properties of the system based on the properties of the matrix of the coefficients. This is really important because next we will study systems, linear systems of differential equations, and the stability properties of these linear systems will depend on the properties of the matrix of the coefficients. Okay, so what is a linear system of differential equations, by the way? Just to understand that what we are doing matters for dynamic analysis. A linear differential equation is, with constant coefficients, is x dot is equal to, let me write this in this way now, let me bring the coefficient on the right, okay? So you remember our original form was this one, x dot plus ax equal to b. So basically it is x dot is equal to minus ax plus b. Coefficient. Now suppose that you want to model the evolution not of one variable, of two variables. And in this case, we have that the state of variable x affects its strength, okay? It affects its time derivative. But suppose that we have a situation in which we have two variables, x1 and x2, and the state of both variables at a given point in time affects the evolution of both variables. So there is a joint effect, okay? The two variables affect the evolution of both variables, okay? So x dot 1 would be equal to some coefficient times the state of x1 plus another coefficient times the state of x2. So both x1 and x2 affect the evolution of x1, okay? At the same time, both x1 and x2 affect the evolution of x2, okay? You will see that we can write, this is a simple model, but we can also have forcing terms like this b. b1 in the first equation, b2 in the second equation. Okay, so this means that the evolution of the two variables is driven by a linear system of equations that can be written in this way. X dot 1, x dot 2, the vector of the time derivatives, is equal to a11 x1, sorry, a11, matrix notation, a11, a12, a21, a22 times x1, x2 plus b1, b2. That is, x dot, the vector of the time derivatives, is equal to A, the matrix of the coefficients, times x, the vector of the states, plus B, the vector of the forcing terms. Why is that? Because if you develop this, here you are establishing the equality between a two-dimensional column vector and this. The result of this set of operations is again a two-dimensional column vector. Why? Because 2 by 2 times 2 by 1, the product here is a 2 by 1 vector. This is again a 2 by 1. The sum of two vectors, column vectors of dimension 2, is a vector of dimension 2. So it makes sense, okay? Now, the first element will be equal to the first element of the vector on the right, which means that x dot 1, compute the product here, a11 times x1 plus a12 times x2 plus b1. Okay? This is the first row, so the first element of the vector, which is the product of the two. It is this one. What about the second? X dot 2 must be equal to the product of the second row here times the vector of the state plus b2. But imposing an equality between two vectors means element by element. Two vectors are equal if the corresponding elements are equal to each other. So this means that both this one and this one must hold together. So it is a system. So our system of differential equations, linear autonomous differential equations, can be written in matrix form. The right-hand side is basically a linear system, okay? So this is why we have to understand, you will see, we have to understand the solution to this linear system. So here is an example of an algebraic linear system, not a system of differential equation. This is a linear system with n equations and n variables. We focus on squared linear systems. Matrix of the coefficient has n by n dimension. It has n rows, n columns. This is a familiar, I guess, algebraic linear system. We can rewrite this system as the product of the matrix of the coefficients times vector x1, x2. Okay? x1 minus 2x2, x1 minus 2x2 equal to 3. 2x1 minus 1/2 x2 is equal to minus 2. So this is the matrix form of the linear system. It is a 2 by 2 system in this example. It has two equations and two unknowns. Most likely, in general, a system with the same number of equations and unknowns has one solution, in general. You may remember this from high school, also from the bachelor degree. In general, it has one solution. What is the necessary and sufficient condition for this system to have a unique solution? The sufficient condition for necessary sufficient condition for this system to have a unique solution is that the determinant of the coefficient matrix is different from 0. Okay? If the determinant of the coefficient matrix is different from 0, we have a unique solution. And this unique solution can be computed in this case manually by substitution. It can be computed with other rules. One is the matrix inversion rule, and the other one is the Cramer's rule. If you want to see how this works, you should look at the extended versions of the slides. I will show you here how to compute the solution with the three methods: Cramer's rule, matrix inversion rule, and substitution, just as an example. But you may know all of this already. Do you already know all of this? Do you remember? I guess you remember how to compute the solution by substitution, by elementary substitution method. There are two more rules. One is the Cramer's rule, and the other one is the matrix inversion rule. So basically, let me go for a moment to the extended set of slides. But what is important here is that when you have a system with n equations, n unknowns, so a square system, square coefficient matrix, in general you have one solution, and the necessary and sufficient condition for a unique solution is that the determinant of the coefficient matrix is different from 0. Okay? 1 minus 2, 2 minus 1/2 has a determinant which is minus 1/2 plus 4. So this is, I guess, 7/2. It's not 0, okay? So in this case, the system has a unique solution. Okay, let me show you how to solve this system first. Let me go to the set of extended set of slides. One moment. Determinant. Look how the Cramer's rule works. This is one possible rule to solve a system with n equations and n unknowns having the coefficient matrix with a non-zero determinant. So suppose that we have this system. A11x1 plus A12x2 equal to B1. A21x1 plus A22x2 equal to B2. You know that we can write the system in matrix notation AX equal to B, where A is the coefficient matrix and B is the vector of the constant terms on the right, okay? X is the vector of the two variables. Suppose that you want to solve this by substitution. What would you do? Go back to our example here, which was in the other set of slides. So let me solve this. Okay, so x1 minus 2x2 equal to 3. Let me go here. The first equation, and the other equation was 2x1 minus 1/2 x2 equal to minus 2. When you solve by simple substitution, you just try to obtain one variable from one equation. And then to replace this into the other equation, okay? So it becomes 4x2, 2x1 becomes 4x2 plus 6 minus 1/2 x2 equal to minus 2. Now, focus on the second equation. 4 is 8 over 2 minus 1 over 2. It's 7 over 2. And this is equal to minus 2 minus 6 minus 8. Okay? Which means x2 is equal to minus 8 times 2 and minus 16 over 7. Okay? And then when you have x2, you put this here, and this becomes minus 32 over 7 . Three is 21 over 7, so minus 32 plus 21 is, if I'm not wrong, minus 11 over 7. Is that okay? Now, go back to the coefficient matrix. 1 minus 2, 2 minus 1/2. Compute the determinant of this, which is the determinant of our matrix A. This is minus 1/2 plus, this is minus 1/2 plus 8 . So this is basically equal to minus 1/2 plus 4. So plus 4 here. Which means minus 1/2 plus 8 over 2, which is 7 over 2, okay? Now, wait a moment. When you go to a general model, a general matrix, it is here, right? Not here, it is here. You have a general matrix, you do the same. You obtain x1 or x2 from the first equation. So you write, for instance, x1 equal to something. You replace x1 here. You have an equation only in x2. Okay, you solve for x2, you go back, and you obtain also the value for x1. If you do this is a useful exercise, you get this. I mean, we don't have numbers. We have x1, x2 correspond to these formulas. They are two fractions. In the denominator of the fraction corresponding to the values of each unknown in the solution, we have a11, a22 minus a21, a12. Both here and here. So the denominator is the same. So what is this? This is just a determinant of the coefficient matrix A. So basically, when we have a square matrix, a square system like this one, the solution for x1 and x2 is a fraction. In both cases, in the denominator, we have the determinant of the coefficient matrix A. What is in the numerator instead? In the numerator is b1 a22, for the first variable is b1 a22 minus b2 a12. What is this? Imagine that you take the coefficient matrix here. We are dealing with the first unknown, unknown number 1. You take the coefficient matrix, you eliminate the first column, and you replace this with the column b1, b2. Okay? So imagine that you modify this matrix. It is this one. Compute the determinant of this. It is b1 times a22 minus b2 a12, which is precisely the numerator here. Okay? Take the other unknown, x2. Take the coefficient matrix. Now eliminate the second column. Replace this with b1, b2. Compute the determinant. You have this one. Okay? So basically, with this rule, which is called the Cramer's rule, the two unknowns can be determined immediately as the ratios between two determinants. In the denominator, we have the determinant of the coefficient matrix, and in the numerator, we have respectively the determinants of the modified matrices, each obtained by replacing the corresponding column with b1, b2, or with the factor b. So this is the Cramer's rule, how it works. So for instance, in our example, we could obtain if this is correct, because if I didn't make any mistake, we can obtain the solution also in this way. The coefficient matrix A was equal to 1 minus 2, 2 minus 1/2. Okay? And I want to compute the determinant of this coefficient matrix, which was minus 1/2 plus 4, it was 7/2, right? Now, take the modified matrix in which we replace the first column with the column B. Let's call it A1 with a tilde. 1 means because that we replace the first column, okay? And it is associated to the first unknown. Okay, so go back. The constant terms are 3 minus 2. So the matrix becomes 3 minus 2, first column. And the second column is the same as this. Minus 2, minus 1/2. So what is this determinant? It's minus 3/2, minus 4. Okay? Right? Because it is minus 2 times minus 2. So minus 4, this becomes 8, so minus 11/2. Now take the ratio between this and this. And this is the value of the unknown x1 in the solution. So it is minus 1/2, minus 11/2, sorry, over 7/2. So it is minus 11/7. So is it okay? Is that the same as we computed? Okay, it is this one. Now do the same with the second variable. Compute A tilde 2. Replace, that is, use this, but replace now the second column with this, okay? So it becomes 1, 2. And the second column is replaced by 3 minus 2. Compute the determinant, it is minus 2, minus 6, it's minus 8. X2 is equal to minus 8 divided by 7/2, which is minus 16/7, which is the value of the other variable, okay? So this is the Cramer's rule to compute the solution of a linear system. And of course, it is the ratio between two determinants. The value of each unknown is the ratio between two determinants. Denominator for all of them, determinant of the coefficient matrix. Nominator, determinant of the coefficient matrix in which you replace the corresponding column with the column B. This works also for 3-dimensional, 4-dimensional systems, and so on and so forth. Another way to compute the solution, which is more important for working out linear systems analytically, is with the inverse matrix method. So when I have a square matrix A, okay, square matrix with dimension n, and this has a determinant which is different from 0, I can define matrix A minus 1, which is the inverse matrix of A, as the matrix such that, so it is defined in this way, A minus 1 times A, or equivalently A times A minus 1, another case in which we have commutative property, equal to identity matrix of order n. By the way, the inverse of a number, if it is different from 0, look at the similarities. The determinant must be different from 0, our real number must be different from 0. What is the number A minus 1? It is defined as the number such that A minus 1 times A is equal to 1. And you know that with real numbers, A minus 1 is just 1 divided by A, okay? Clear? So it is exactly the same definition. So, you know, in principle, when you want to compute the inverse matrix, when we want to compute the inverse matrix of a matrix, we should find matrix A minus 1 that multiplied by A gives the identity matrix of order n as the result. Of course, we don't do this. We have rules to compute inverse matrices. In particular, in the case of a 2 by 2 matrix, A11, if our inverse matrix is A11, A12, A21, A22, okay, the inverse matrix is like this. Exchange the two elements in the main diagonal, change the sign of the remaining elements. Okay? If you're not convinced, try to compute A minus 1 times A, defined in this way. Okay? Now, of course, this is the inverse matrix, but this is not the inverse matrix. This is the determinant times the inverse matrix. Now you have to divide by the determinant of A. So the structure of the inverse matrix is like this. This is the original matrix. The inverse matrix is this one divided by a scalar, or multiplied by a scalar, better, which is 1 over the determinant of A, okay? So let me show you that the product between A minus 1 and A is consistent with this rule. Look at the product. It is A22 times A11 minus A12, A21. Now, A22 times A12 minus A12 times A22, which is 0. Minus A21, A11 plus A11, A21, which is again 0. And now this times this is minus A21, A12 plus A11, A22. So it is again A11, A22 minus A12, A21. So what we learn here is that the product between a matrix and its inverse is a square matrix having the determinant of A, this is the determinant of A here, 0, 0, and the determinant of A. Okay? So we have learned that A minus 1 times A is equal to this one. This is not A minus 1, this is this one. This matrix here, which is A minus 1 times the determinant of A, okay? This matrix is A minus 1 times the determinant of A, okay? If you do that, you obtain that determinant of A times A minus 1 times A is equal to basically a square matrix, which is scalar. It has the determinant of A times the matrix identity, okay? So basically, we have shown that this is, okay? So the product of a matrix and its inverse is the identity matrix. And in 2 by 2 matrices, this means that if you take this matrix, you exchange the two elements in the main diagonal, and you take the opposite of the remaining elements, the negative of the remaining elements, you obtain, and you divide by the determinant of A, you obtain the inverse matrix, okay? So this is the rule to compute the inverse matrix in this case. Now take the matrix of the coefficients of the previous example. The matrix of the coefficients of the previous example was this one, okay? Sorry, this was the determinant. The matrix was 1 minus 2, 2 minus 1/2. So if A is 1 minus 2, 2 minus 1/2. Okay? We know that the determinant of A is equal to minus 1/2 plus 4, 7 over 2. What is the inverse of matrix A? We have to divide by the determinant and then multiply by this matrix in which we exchange the two elements in the main diagonal and we take the negative of the remaining elements, okay? And remember that this one is 2 over 7. 1 over determinant of A is 2 over 7. So what is the result? 2 over 7 times minus 1/2 plus 4. Minus 1/2 plus 4 is 7. No, this is, I mean, so I want to compute the inverse matrix, of course. So this becomes, we can also leave this expressed in this way, but if we want to solve this, we obtain minus 1/2 times 2 over 7, which is minus 1 over 7, 2, 4 over 7. This becomes minus 4 over 7, right? And this becomes 2 over 7. Okay, so this is the full expression for the inverse matrix, and this is the expression of the inverse matrix in which we use a product between a matrix and a scalar. Okay, is that okay? So this is minus 1 over 7, 4 over 7, minus 4 over 7, and 2 over 7 again. Now, look at this inverse matrix. Take our original system. Our original system was AX equal to B. What is X, the solution? We can solve this by simple substitution, by Cramer's rule, but we can also do this left multiply both this side and this side by the inverse matrix. This becomes identity matrix times X equal to A minus 1 times B. But the identity matrix times X is just X. So we have the solution as the product of A minus 1 times B. Okay? Let us see if it works for our example. We know that X must be equal to, which is the values of the unknown, x1, x2, must be equal to A minus 1, which is this matrix. We can also write this in this way. It is much more interesting to work out matrices, also in the case in which we leave the matrix expressed as the product with a scalar. Use this, you can use this or this. So it's 2 over 7 times minus 1/2, 2, minus 2, 1. Times B. What was B? B was, vector B was equal to, I don't remember. Vector B was 3 minus 2. Perform the computations. 2 over 7 remains a factor. Minus 1/2 times 3, minus 3 over 2. minus 4, the first element of the vector, minus 3 over 2 minus 4, and this becomes minus 6 minus 2. That is 2 over 7. This becomes minus 4 is minus 8 over 2, so minus 11 over 2 minus 8. And this becomes, as a final result, minus 11 over 7. Okay, multiply this times this, and minus 16 over 7. Okay, so in our example, so this is called matrix inversion method to solve linear systems with a square coefficient matrix. Matrix inversion method, and the solution is this one, which is the same as the one we obtained with the Cramer's rule, which is another method to solve linear systems. And of course, there is also the simple substitution method. Okay, so what is the most, I mean, if you have a system of dimension 10 by 10, you don't solve it manually, okay? So there are just a few lines of code to solve the system with some application, MATLAB and whatever, okay? If you want to work out analytical models in which in the coefficient matrix of the systems there are, for instance, parameters, and you want to understand something about the behavior of the solution, you generally have low-dimensional systems, dimension 2, dimension 3, and you can use both simple substitution. And in the case of low-dimensional systems, dimension 2 or 3, I strongly suggest the Cramer's rule, because it's very easy to compute determinants and to take the ratio between determinants, okay? It's very easy. I don't suggest the simple substitution method unless you have the case 2 by 2. Instead, the matrix inversion method is not used for computations, for manual computations, but it is really important for analytical treatment because, you see, it allows us to write down the solution analytically. You see here that in principle, we can write down the solution of a system with an analytical formula, which is this one. X is equal to A minus 1 times B. And then suppose that you want to use this X to perform other operations. You know that this is a solution of the system, you can use this. You can use this expression, perform other operations, work out analytically your solution because you need it to as the input of some other part of your model. So for analytical purposes, matrix inversion method. For manual applications to simple low-dimensional models, Cramer's rule. Simple substitution is not suggested unless you are in a two-dimensional case, okay? So this is basically what I wanted to show you. In the next part, I will show you just after the break, after a 15 minutes break, I will show you how we can characterize the solution of a system in the case of infinitely many solutions, which is the case we need for eigenvalues and eigenvectors. Okay, so break. We take a 15 minutes break. Okay? Okay, so now the main point here is that we will deal with systems where B is equal to 0. Let me just show you, go back and show you one, and emphasize and highlight, stress one thing. We are dealing with systems of this type. This is a square matrix. This is a vector of the unknowns, and this is the vector of the constant terms, okay? We know that if and only if, this means if and only if, the determinant of matrix A is different from 0, if and only if this happens, then the system has a unique solution. This solution can be written in this way. Clearly, it is unique because it is the product of matrix A times vector B. It is a unique solution. If you remember the structure of matrix A in the two-dimensional case, you understand that matrix A exists if and only if the determinant is different from 0, because if you remember, the matrix A has the determinant in the denominator. It is a constant, okay? It is 1 over the determinant of A. Remember the formula? In order to compute the inverse matrix, clearly the determinant of the matrix must be different from 0. Otherwise, we don't have any inverse matrix. Otherwise, our matrix is not invertible. Now, it's clear that if A minus 1 is a matrix which has the same dimension of A and by n, and you multiply a matrix which exists if the determinant is different from 0, you multiply it by B, you get a vector. And this vector is the unique solution to our system when, of course, the determinant of A is different from 0, okay? Now, suppose that B is 0, the 0 vector, so B is 0, 0, in the case of a two-dimensional system. So we have this A times X equal to 0. Okay, suppose that the determinant of A is different from 0. From the previous point, we know that we have one solution. One solution. What is the solution in this case? You know that the solution is A minus 1 times B, which is equal to A minus 1 times 0, which is equal to 0. Okay? So if in particular our system has B equal to 0 vector, and our system is one with a unique solution, when the determinant is different from 0, this unique solution is necessarily 0. Okay? A solution 0 of this system, which is called linear homogeneous system. Homogeneous because B is 0. When a linear homogeneous system with square matrix A, with determinant different from 0, the system has a unique solution, okay, which is the 0 solution. This solution is called, of course, the trivial solution. Trivial solution. So a linear homogeneous system with matrix A invertible, with matrix A with determinant different from 0, has only the trivial solution. Okay? But in the case of the solution to linear system of differential equations, what is important is the case in which our matrix has more solutions besides the trivial solution. Okay? So the point is that we are interested in understanding conditions under which the determinant is equal to 0. Because if the determinant is different from 0, there is only the trivial solution, okay? In order to have more solutions, we need our determinant to be different from 0, to be equal to 0, okay? To be equal to 0. So this is the main point. Now, here is a summary, a schematic scheme, a summary scheme. If we have a system which is homogeneous linear system, Ax equal to 0, we know that x equal to 0 is a solution anyway. X equal to 0 is a solution anyway. It is called the trivial solution. If the determinant is different from 0, x equal to 0 is the unique solution. If the determinant is equal to 0, there are infinitely many solutions, including the trivial one. This will be the case where we focus in the next set of slides, which is about, this is a crucial point, about the eigenvalues and eigenvectors of a square matrix, which are basically what we use to compute the solution to linear systems of differential equations. So basically, let me show you, just to let you know what happens with the solution to linear systems of differential equations. Remember that if we have a linear differential equation with constant coefficients, we have x dot is equal to minus ax plus b, right? When we have a system of linear differential equations, we have x dot vector is equal to ax, where A is a matrix, plus B. What characterizes the solution in the case of a linear equation? It is this coefficient, minus A, okay? We could call it A, because by analogy, but it is this coefficient. Minus A determines whether it allows us to write down the solution, and it determines whether the solution is stable or not, right? The instability of our solution. Okay, but here we don't have a coefficient, we have a matrix. Okay? A is a matrix, but by analogy, this matrix determines the stability or instability of our solution and allows us to write down the solution. But here it is easy because we have a number here. And here we have a matrix. We have to extract numbers characteristic numbers from this matrix. They are called characteristic roots of the matrix that play a role similar to A or minus A in the simple equation, okay? These are called eigenvalues. Of the matrix. And we will see that each eigenvalue is associated to a set of eigenvectors. Both of them will allow us to write down the solution by analogy with A here. In particular, the eigenvalues will affect the stability of the solution. Okay? And this is what we are going to do now. I divide this in two steps. Today, I will just show you what are the eigenvalues of a square matrix. Next week, I will use the eigenvalues to write down the solution to a linear system of differential equations. What are the eigenvalues of a square matrix? This is a set of slides that I prepared just for your for this part. It's very short set of slides. It's the basic things. It is on another textbook, which is, maybe it is among the suggested textbooks, but you don't need to look at the textbook. Just look at the slides. There is a definition and a few examples on eigenvalues and eigenvectors of a square matrix, okay? Please, try to understand as much as you can on this very short set of slides, because everything is here, okay? So I'm going to show you, technically speaking, there is nothing. You only have to understand what is the meaning of these eigenvalues and eigenvectors. Computationally, there is nothing difficult. We have three elements: a square matrix, A, a scalar, that is a number lambda, and an n-dimensional vector x. An example: A is 3 minus 1, 4 minus 2. The scalar is minus 1. Our vector is 1/2, 2. I selected three elements to show you that these three objects jointly have a very important property. We can check immediately that if I multiply matrix A by this particular vector x, I obtain, of course, what? A two-dimensional vector. Again, AX is a two-dimensional vector, okay? And it is the same two-dimensional vector that I obtain if I multiply the scalar lambda by vector x, okay? And this means that when it comes to this particular vector x, multiplying -1 times x gives the same result as multiplying this matrix times x. Okay, so these three elements jointly have this property. Basically, for this particular type of operation, the scalar lambda -1 plays the same role as matrix A. Okay, because the result multiplied by vector x is the same. But just for this particular vector, okay, it works only for this particular vector. Okay, so what we say, you can check this. You can multiply A times x, and then lambda times x is easy because it is -1/2 minus 2. Okay, -1/2 minus 2. Multiply A times x, matrix product, you get -1/2 minus 2. When this happens, we have three objects, okay? A matrix, square matrix, a scalar, and a vector. When this happens, when these elements jointly have this property, we say that lambda equal to -1 is an eigenvalue of matrix A, and the vector, 1/2, 2, is an eigenvector associated to the eigenvalue lambda equal to -1, okay? This is just an introductory example. Of course, the next problem will be, okay, I have a square matrix. I would like to find out the eigenvalues of this square matrix, of these characteristic numbers. They are called characteristic roots. Okay? In a sense, they summarize the properties of this matrix. They summarize the behavior of this matrix when we use this matrix to multiply some specific vectors, okay? We would like to find out the eigenvalues of the matrix, and for each eigenvalue, find out what are the associated eigenvectors. Is that clear? How can we do? A little bit of linear algebra, what you already know from basic matrix operations, and the properties of linear systems homogeneous, okay, homogeneous linear systems, help us to solve our problem. So the definition is this one. A is a square matrix. We say that a number lambda is an eigenvalue of A if there exists a vector x. This must not be a trivial vector, must not be 0, such that multiplying A by x is equivalent to multiplying lambda by x. Okay? We neglect vectors x equal to 0 for a simple reason. If you take a vector equal to 0, this is 0 and this is 0. Okay? So it doesn't make sense to find out the eigenvalues of a matrix in the case of a 0 vector, okay? So we want to know whether there are numbers lambda, so-called eigenvalues of A, that have this property, okay? Lambda is an eigenvalue of A if there exists a non-zero vector x such that using lambda as a scalar to multiply x is equivalent to using matrix A to multiply x. This is the meaning of the definition. In this case, we call x an eigenvector of A corresponding to the eigenvalue lambda. And we will see that there are infinitely many eigenvectors associated to a given eigenvalue. So basically, we will find a limited number of eigenvalues, for instance 2, in the case of a square matrix, 2 by 2. And for each one, there is a family of eigenvectors, infinitely many eigenvectors associated to each eigenvalue. Now, how can we find lambda and x? So this is the main point that uses a little bit of algebra. We have to start with this property that defines the eigenvalue and the eigenvectors. So A times x is equal to lambda times x. I rewrite this in this way. A times x is equal to lambda times x, but x can be regarded as the identity matrix times x, okay? So this is I and x is x by the properties of the identity matrix. Next, I move this to the left and I change the sign. Ax minus lambda identity x equal to 0. Just move to the left, okay? It is easy. Now, here there is a common factor, which is x. X here, okay? So I can factor this in this way. This is called, this is a very simple, it's called distributive property of matrices. Of the matrix product, it works like for numbers, okay? It's a distributive property. So A minus lambda identity, remember that lambda identity is a n by n matrix, okay? Lambda identity is a n by n matrix. A minus lambda identity, which is a new matrix that multiplies x, is equal to 0. Now, don't worry about the name of this matrix, A minus lambda identity. Call this B. You have B times x equal to 0. It is an n by n matrix times x equal to 0. We are not interested in the 0 vectors x. We know that this linear system has 0 as a solution. This is the trivial solution. We are not interested in this. We are interested in non-zero solutions. But what is the condition by which this system, this is a linear system, can have non-zero solution? Go back to the previous property of linear system, linear homogeneous system. This system will have non-zero solutions, so non-zero vector x, only if the determinant of the coefficient matrix B is 0. Otherwise, if the determinant is different from 0, it will have only the 0 solution, but we are not interested in this case. So the only situation we have to explore is when the determinant of B is 0. Okay? This is a key point. So in order to have solutions, x that are different from 0, the system must be in the case of infinitely many solutions. We must be in the case of infinitely many solutions. That is, determinant of B equal to 0. Okay? B, remember that B is A minus lambda identity of the shootable dimension F. We must write this equation, determinant of A minus lambda identity equal to 0. Okay? Or equivalently, determinant of lambda identity minus A equal to 0. Okay, so you can also just change the sign to your matrix, and the determinant is basically, it's a simple property. If you change the sign to your matrix, you change the sign of the determinant, but you are just interested in when it is equal to 0, so it doesn't matter. You can write this in this way, A minus lambda identity, or lambda identity minus A, okay? Some textbooks use this, some use this, but the solutions to this equation is the same in both cases. So basically, if you have your matrix A, you want to find the eigenvalues, you just have to compute the determinant of A minus lambda identity, which is the sum, algebraic sum between two matrices. In one matrix, the unknown lambda appears. You compute the determinant of this, you set it equal to 0, you solve the equation, and you find the eigenvalues of the matrix. So this is the equation that characterizes the eigenvalues of A. In fact, it is called characteristic equation. And the eigenvalues are called characteristic roots. Here is a very simple example with our matrix, which shows how it works. A is our matrix, 3 minus 1, 4 minus 2. First, I have to build my lambda, A minus lambda identity, which means, remember that lambda identity is a scalar matrix, it is this one. So I have basically to change the sign, I have to subtract this element by element. So the only elements that become modified are the elements in the main diagonal, okay? So you would get 3 minus lambda, minus 1, 4, minus 2 minus lambda. Or equivalently, you can use lambda identity minus A, and you would get lambda minus 3, 1, minus 4, lambda plus 2, okay? So this is lambda identity minus A matrix. Now you have to compute the determinant of this, and you see that since the matrix is 2 by 2, the determinant is a quadratic polynomial. Why is that? Because it's lambda minus 3 times lambda plus 2 minus 4, so plus 4, okay? So basically the characteristic equation for matrix A is a polynomial, is an algebraic equation of the same order as the dimension of your matrix. A 3 by 3 matrix, it's a third order polynomial, so a third order equation. An equation of degree 3, a third degree polynomial. In the case of a 2 by 2 matrix, we have a quadratic polynomial and the quadratic equation, algebraic equation, okay? So we write the equation. We write this in standard form, lambda squared minus lambda minus 2 equal to 0. Apply the usual solution formula. It has two roots, minus 1 and 2. Okay, so these minus 1 and 2 are the eigenvalues of matrix A. By the way, in the introductory example, we had minus 1, okay? We explored the case of minus 1, and we found one eigenvalue of this. We had one eigenvalue given by my main example. In fact, there are two eigenvalues, minus 1 and 2. In general, if it is an nth degree polynomial, we may have n solutions, okay? So now we have these two eigenvalues. We want to find the eigenvectors associated to each eigenvalue. There will be infinitely many eigenvectors associated to each eigenvalue. It is clear why, because since now we use these eigenvalues, so in the system we replace lambda with these eigenvalues, but these eigenvalues were found under the assumption that there are infinitely many solutions to the system. So if we use these numbers, minus 1 and 2 here, we will necessarily have a system with infinitely many solutions, okay? We want to find the infinitely many solutions associated to each of the eigenvalues. So this is really easy. It is enough to solve this system in which A is given, lambda just found, replace lambda, build the matrix B equal to A minus lambda identity, or lambda identity minus A, solve the system. So what are, for instance, the eigenvectors associated to the first eigenvalue? Lambda 1 equal to minus 1. We have to write down the equation lambda 1 identity minus A times x equal to 0. Now, lambda 1 identity minus A, lambda 1 identity is basically our identity matrix in which we have replaced the main diagonal with the first eigenvalue, lambda 1. Okay, minus A was this one. We compute our matrix, lambda identity minus A. We multiply this by the vector, and we impose that the result is 0. We can write this explicitly. It becomes minus 4x1 plus x2 equal to 0, and again, minus 4x1 plus x2 equal to 0. In general, when we do that, we see that the two equations are redundant. In fact, there is only one equation, okay? And this is the reason why we have infinitely many solutions. We don't have really two equations. We have two unknowns, but one equation, in fact. And this is the reason why we have infinitely many solutions. We can find the solution in this way. x2 is equal to 4x1. But if, in general, you can replace this into the other equation, okay? Here, it is just useless, because the second equation is exactly equal to the first, or it is proportional to the first equation, okay? In general. So basically, the only information that we have is that any vector satisfying this property works. So any vector in which the second component is 4 times the first component works. We can write the family of these vectors in this way. The second component is 4 times the first component. So it's 1, 4 multiplied by an arbitrary factor, real number alpha, okay? Where alpha is any real number, of course, different from 0. Why different from 0? Because otherwise we have the 0 vector, which is the trivial one. We don't want, we neglect the trivial solution, okay? So any vector with this structure, any vector, and they are infinitely many, any vector with this structure is an eigenvector associated to the eigenvalue lambda 1 equal to minus 1. Okay? The second step is to find the eigenvectors associated to the other eigenvalue, which was 2. Okay? So by the way, our vector of the initial example has the structure, you see? It's the second component is 4 times the first component, okay? So here alpha is basically 1/2 in our example. We found the whole family of vectors here. It's alpha times 1, 4. What about the second eigenvalue? The second eigenvalue is 2. Okay. Now, I do the same. I compute here lambda identity minus A. Okay. But now lambda identity is lambda 2 identity. So it has 2 here, not minus 1, minus 1. I have to replace the new eigenvalue, 2, 2. I subtract A, and I obtain my matrix B. And my matrix B is this one. Minus 1, 1, minus 4, 4 times x1, x2 equal to 0. Again, as expected, you see that there is, we have formally two equations, but one is useless, because the second one is basically the first. Because the line is proportionate to the other line. So what do we get here? Minus x1 plus x2 equal to 0. And then minus 4x1 plus 4x2 equal to 0, which is the same equation multiplied by 4. So here we get x2 is equal to x1 from the solution. So any vector having the second component equal to the first component works, which can be written in general as beta times 1, 1, this basic vector, let's say, beta times 1, 1, with beta different from 0. Just remember, here I write the solution as beta times the simplest possible vector of this family, of course, okay? But it is the same writing beta times minus 3, okay? Because beta is arbitrary, okay? So you can just write one vector of the family here and multiply by a constant. Next, the next step is, and then this is also the last step for today, basically, it is the representation in the plane of the two eigenvectors, which is very useful for the graphical analysis of associated linear systems of differential equation. Vectors of belonging to this family, okay, they are infinitely many. But this doesn't mean that any vector is a solution. They must have this property. The second component is equal to the first, okay? If I represent these vectors in the plane x2, all of these vectors constitute a straight line of equation x2 equal to x1, which is what is written here, x2 equal to x1. So the second coordinate is equal to the first coordinate. It is a straight line. It is the bisector of the first quadrant, okay? The other eigenvectors were x2 equal to 4x1. So I represent this in the plane as a straight line of equation x2 equal to 4x1, okay? So basically, in the two-dimensional case, by representing the solution, the eigenvectors in the plane, I get these two straight lines. This one is associated to the eigenvalue lambda 2 equal to minus 2. This one is associated to the eigenvalue lambda 1 equal to minus 1. Okay? Each eigenvalue has an associated line in the plane. Is that clear? So this is all what you need, basically. Eigenvalues and eigenvectors of a square matrix. If you look at the next slide, but I will use it next week because it's a short. It's a trick to compute immediately the eigenvalues. And instead of building this, instead of building this matrix and computing the determinant and setting the determinant equal to 0, I can just work on matrix A, forgetting about this one, and just work on matrix A and using the trace and the determinant of this matrix. The proof is very easy. It's in the last two slides, but I don't explain it today. I will explain it next time because it's strictly related to the solution to our systems of differential equations, okay? So basically, we can just solve this equation. Lambda squared minus trace of matrix A times lambda plus determinant of matrix A equal to 0. So this is the characteristic equation. You can just write down the characteristic equation based on the coefficients of matrix A without building A minus lambda identity and computing the determinant, basically, okay? It's really a short solution for this, for arriving at the characteristic equation. So these are the eigenvalues. Next time I will show you. First I want to propose you a summary exercise on what is required in terms of abilities of matrix algebra, solving problems of matrix algebra. And next I will use eigenvalues and eigenvectors to model the solution to linear systems of differential equations with constant coefficients. Okay, thank you, and see you next week. Bye. Have a nice weekend.
Thank you. Bye.
Bye.
Bye-bye.